A group can have representations of any dimension, meaning that it can act on any dimensional dynamical system. So here is a one-dimensional example. Which you will find bewildering, strangely enough. So let's take a unit interval, or double unit interval, from -1 to 2 to +1. And we call this our dynamical state. So now, which means, dimension of your state space is d equals 1. Very simple thing. So if I measure where I'm on a line, I just measure one coordinate. Let's call it x. And then my law of motion, in this case I can draw the law of motion in the plane because it'll give me what happens as I apply my map in one iteration. This I'll call xn plus 1, and that's just my dynamical law applied to previous state. So these are two one-dimensional things. I can plot it as a picture. And this is the last time that I can actually visualize dynamics, because if I have this map and I try to do the same trick, I go from plane to plane, which is 2 dimensions to 2 dimensions. So I have to draw a plot of these 4 dimensions, and most of us don't know how to do that. And here is the map that we'll use. So I can think of this square where horizontal position where I am now and vertical position where I'm 1 unit of time later. And for example, I can decide that if I'm here, 1 unit of time later I'll be there. So just have a law that says in the neighborhood I expand with some slope. So in one iteration I'm further away. So this slope is larger than 1. It'll be 1 if it's diagonal, so it's obviously larger. And then if I'm in this interval, I write a different thing. So I go like that. And if I'm here, I go like that. And now you have to scratch your head a little bit and tell me whether you understand it, because this thing you understood, which is much harder. But this one you will find somewhat baffling. So are you okay with this map? Do you know what it does? So it says any place around here. So from here I can divide my world into 3 regions. So this region here, which I'll call central region MC, so this interval. If I'm in this region, then what happens is this linear map applies. So x just gets multiplied by the slope of this map, and because slope is larger, x gets further away. On this side, which I'll call M right, what happens is that if I'm exactly at this point, in one iteration, I'm at -1. But if I'm any place around here, for example, in this point, this is a fixed point in one iteration where I used to be. And if I'm this interval, then I get further toward the edge in one iteration. And there is an interval like this, the left interval. So the map can be thought of 3 separate maps. The space is divided into 3 subspaces. So M is the union of M left, correct? And the unions, and actually, and that's fuzzed over in the book, and I'll be grateful if you help me clean it up. You also care about the fact that these things overlap, so that these points here belong to both sets. So border points are very important. So how does invariance of the law of nature works in this case? So for example, if I start here, and again, please stop me if you don't understand how the one-dimensional maps works. I mean, it's important and we'll use it a lot. So if I start at this value, call it x0, then what happens is I evaluate it. So this is x1. Time has increased by 1 step. And then I want to use x1 as the initial point for the map. The way I can do this is I look at where the diagonal is and I use it as a starting point. So this is x0. This is x1. Do you understand me? In time. It's really important to understand this. I'm sorry, but and it's funny that this is a mental block. And now, I'm sorry, but I'm not written this very well. So this is x3.
Sorry, here what is the space of the dynamical system? Is the
Unit interval. Double unit is from -1 to 1 is being mapped into -1 to 1. So you're mapping this axis into this axis. I don't know what the word surjective means, but what does it mean?
I mean, it's not 1 to 1, no?
It's 1 to 1 forward, but not backwards.
So that's surjective.
So it's like not...
It's not diffeomorphism. Yeah.
It not define a map of that.
You can go back. You have 3 pre-images going backwards, but you go forward. It's important. So that's why we always talk about semi-groups. It's a perfectly good dynamical system, but to go back, you have to specify which paths you want to pick from 3 possible paths. Because there are 3 intervals, there are 3 maps, and if I look here, this could be a path, this could be a path, this could be a path. So it's only forward iteration. So, I just drawn one solution of the system. You go from here, you go to there, you go to there, and this was 2, and you end up there. So this is one trajectory. 2x3. So now the first statement of symmetry says that if I have one solution that does this, this should be a solution in which initial point is flipped. So the first statement, 1. If f of 3 is solution, so is f of 3 at G. Now the symmetry is very simple. G consists of identity, and I've designed this map in such a way that if I flip this axis and this axis, it map into itself. So it's an antisymmetric map, and result is also antisymmetric. So it's a group of 2 element called permutation on 2 elements, or cyclic permutation of 2 elements, or dihedral group 1. It has all kinds of names. Or Z2, if you're applied mathematician, or whatever. So for these very simple groups, they have lots of names, but later on they get more specific. So the first statement of symmetry means that if I look at the image of this guy, and where does that put me? It puts me here. Let's see, maybe green. So this point is x 0 flipped by sigma. So that means if I was here, I start there. Tuk, right? Start here rather than there. And, I hate drawing figures for this book, Unspeakable Book, because this figure like takes half a day for me to draw, unless you teach me how to draw figures better, but it's a totally trivial figure. So what happens here is, I go that way, and maybe it's better to draw it as a separate picture because it gets too busy. Here's the map. And if I start here, then the thing will look like that. So this is sigma of x0. This is sigma of x1. And then it goes here. Sigma of x2. And sigma of x3. So all the points along the trajectory just flips of the points, so you flip them both ways. So this trajectory started here on dug, is the same as the trajectory started here and going to dug, and they're obviously both good trajectories. So that's the first statement of invariance. If you have one solution, the group will generate all other solutions. Now, group has only two elements. So the first is identity, and the second one is the flip. In this case, there could be 6. In general, there's 6 images of any generic trajectory. Here, there are only 2, because group is only of 2. So there are 2 examples of this.